and that the transmitted equals 2 over alpha plus beta. Wait a minute. That looks really like something we did before. Or if we were in France, we would say, right? That's making me wonder a little bit. These are kind of special equations because this actually is the general case of what we did previously. With the normal ones, at just normal incident. These are known as the Fresnel equations. These are known as the Fresnel equations. For light that's in the plane as you come in, so it's oscillating like this, and it hits a surface. How much is it's coming in at an angle like this, hits the surface. How much of that goes through? How much of that is reflected? This is in the XZ plane here. So it can't have any component out of oscillation for the electric field vector. So it's going to be coming in like this. And notice that's why that has a Z component, because B would be out of the board. E must be in this XZ plane. B is out of the board. So it's oscillating like this, some goes this way, some goes through. Those are the Fresnel equations. They do have them for if it's doing perpendicular, say it's doing like this, comes in, this goes out. He leaves that for you to do. Notice again about the in phase and out of phase. Note, alpha has angle. Say, note, alpha is a function of the incident angle and the transmitted angle. And if you want to look at alpha just in terms, you can put alpha in terms just of the incident angle, and you can get that as cosine of theta incident over the square root. I'm not going to go into this to the N1, N2, so you think you might know where that comes from. Sine theta 1, theta incident. And that, take this whole term and square it. If that's squared, you might want to look at Pythagorean theorem for doing it. Now, if that tells you, all right, if you use this, so just based on the incident angle, now we can look at just based on the incident angle. What's the electric field transmitted? What's the electric field reflected? And we start looking at that, we find a condition where all the light is transmitted and none reflected. Again, remember, we're oscillating. It's a plane wave like this. It's a plane wave. Excuse me. The polar it's a plane wave because it's doing this in this direction, in the XZ plane. But it's polarized, light is polarized up and down relative to its direction of motion here and relative to that boundary. And this occurs when alpha equals beta. You may not be able to see that very well. Okay, this occurs when alpha equals, I'm almost done. And if alpha equals beta, you can derive that. Basically, you can make some assumptions on these angles, and basically you can say that the tangent of this angle, you can call that theta b, is approximately equal to N2 over N1. Or you can say then that theta B is equal to the inverse tangent N2 over N1. Theta B is known as Brewster's angle. Brewster's angle. This is the point where the amount of light, when at a certain, just at one specific angle, at a certain angle, no light is reflected. No light is reflected. So let's kind of look at a graph. If you do a graph of this and you look at the intensities, because intensities, if you look at the intensities reflected, you know, it's the electric field, just like we did previously, it has to be 1/2 permittivity, the velocity in1, E naught R, and that's the magnitude of it, cosine of theta R, because it's a function of cosine now, cosine in this one. It's 1/2 permittivity on E2, the velocity in 2, not transmitted electric field cosine theta t. So what you can do is, if those are reflected and refracted, let's look at a graph. I'm going to put this here. And if you look at a graph, what they basically do is they stop this right here at 90 degrees and at 0 degrees. And this is going to be our incident angle here on the, what we normally call the x-axis. The horizontal axis will be the incident angle. So here is going to be the intensities. The intensities. They're really plotting reflection and transmission coefficients, but I'm going to do it like the book does. What happens is, this is about 0.8, this is negative 0.2, and you're like, right about 60 degrees there. And what they've found is, if you look at, we're going to look at the reflected wave and the transmitted wave as a function of angle. And it starts out, this is the ratio of the transmitted amplitude to the incident amplitude. And it makes sense. At 90 degrees, most of it's, you know, as you get close, as you get at an angle like this, a really what we call grazing incidence comes in. If it comes in just like this, most of it's going to be reflected. Very little. It makes sense for just a ball striking something. If a ball comes in like this at an angle, very little forces in this direction of the ball. Most of it's going to want to keep going that direction. Same kind of with light. Look at it from an energy perspective. If light comes in like this, most of the light's going to be reflected. Very little is going to get through. So that's the ratio of the transmitted to incident. Let's look at the ratio of the reflected to incident. And that one actually looks like this. And there's one up there at the top. Now, how can that be negative and positive? What's going on is when it goes from negative to positive, basically it's changing the, that's when that wave kind of was in phase or out of phase. The electric field may have started out here, and on this side, it would flip over. Actually, here it would be negative. So from an angle from 0 to about 60 degrees, actually it's a little bit in front of 60 degrees. We'll make that 60 degrees. At that angle right there, for whatever material we're at, and this is probably air to glass interface based on what they're using. Let's see if they say here on it. Yeah, he could have been a little bit more illuminating. Get that illuminate light pun. Illuminating on what he used for this to get Brewster's angle. And so here it would actually flip it, kind of build that picture. The electric field vector goes in the other direction. And here it would just stay past that, around 50-some degrees, it would just stay oscillating, stay downward. the electric field isn't 180 degrees out of phase with it. It's just in phase with what happened. Now, you're like, well, how do I know that most of the light, and this is reflected over incident? How do I know that as the angle gets closer to 90 degrees, that most of the light's reflected? How do I know that from reality if I was using a ball as well? Look at a rainy road. Rainy roads with light coming way off, it reflects the light from that road, and you can, it's like you can see it coming at you, especially when it's rainy. In reality, if you look way far off, you can actually see, like bushes on the sides of roads and stuff. I've noticed it if the angle's enough. Even pavement acts as a reflector, and not just a scattering reflector, a mirror type reflector, which is what this is assuming at what we call grazing incident, when that angle gets close to 90 degrees on that incident angle. Now, I do want to look at of course, the reflection and transmission coefficients. Of course, remember those are defined as intensity reflected over the intensity incident over the intent, and the transmission is the transmitted intensity over the incident intensity. Alpha minus beta over alpha plus beta, quantity squared. And notice it's similar before, but that was a special case. This is now the general case. Alpha beta 2 over alpha plus beta, quantity squared. And what you can see is, for this N2 and N1, which in this case is probably an air to glass interface. If you look at a graph here, and now you know these have to be bound between 0 and 1 from what we did last time. We'll make this 90 degrees, put 60 degrees right about here, and 30 degrees right about here. Make that 1, and make that about 0.5. What we find in most of the light, we said about 96%, and that's just normal incidence. What we're going to see is that at an angle, most of the light gets transmitted through if it's in this plane. So it's going to start out, say, right about here. It goes, it pops off the top right about there. Then it goes to none get reflected. And this right here, that's equal to 1. That means all of it's transmitted. So this is the transmitted light. And of course that would be, at this one, for the reflected light, there's really not a hump there, I'm sorry. And then it starts going up to 1, right at 90 degrees. It's not that abrupt, but it's pretty close. There we go. And this is the reflection coefficient. And of course, once the angle gets above about 60 degrees, or so 65 degrees in reality, I didn't make that bottom out enough. So if I really do this right, like that. Once it gets about 70, 80 degrees, close to grazing incident, most of the light is reflected. And that's off of any surface, water-air interface. If it is polarized like this, coming into the surface. So if this was the water, light would be coming in like this into the water. It's polarized in that direction. Not polarized perpendicular to it, so it's fields oscillating like this are different. So you have different reflection and transmission coefficients. They are Fresnel equations for that as well. But this is a lot. I think it's pretty cool. This stuff's only valid for electromagnetic waves because we sort of apply the boundary conditions for electromagnetic waves. The stuff for the laws of reflection, those, remember, are general for any transverse type waves, because that's just based on a transverse wave and its formulation, but not on dealing with the amplitudes. Hope you enjoyed it.